morning, everyone.
Good morning, Professor.
Good morning, Professor.
Good morning, Professor.
Good morning.
Morning.
So today we're going to talk about 3.3, okay, derivative of trigonometric functions, okay. So let's discover the derivative for some trigonometric functions. So we start with this function, y equal to sine of x. So we know the graph of sine of x has a period of 2 pi. So I'm going to draw from 0 to 2 pi. The graph of it is going to be like this. The function value will be 0, 1, 0, -1, and 0 over here. So it's a curve like this. So if you put a person over here, okay, put a person over here, right in the middle, from 0 to 2 pi, then you can have this curve like this. So think about this dance move over here. So if you put a person over here, then your arms will move like this kind of move. Okay, anybody who dance, anybody know this? So I don't know what dance move is that, but you can call that a sine x dance move. So now we're trying to discover the derivative of this function sine of x. Remember, derivative corresponds to the slope of the curve. So let's find the slope of the curve over here. So at this point and this point, the tangent lines are horizontal. So the slope will be equal to 0. When x equal to pi over 2 and also 3 pi over 2, then we will have the derivative equal to 0. So correspond to this point, the derivative of this sine of x here will be equal to 0. Okay, 0 here and 0 here. And then over here, if you look at the slope, then you if I draw it better, you see the slope of the tangent is actually equal to 1. So I have this y coordinate equal to 1 for the derivative over here. And over here also, the y coordinate will be equal to 1 for this corresponding derivative. And then at this point, when x equal to pi, if you look at the tangent line, the slope is -1. So I will go down and then make the y coordinate to be -1 over here. So I got those points, 1, 2, 3, 4, 5 points. And if I can draw more points, I can look at the slope of the tangent at each point on the curve over here. I actually got the curve over here. So the curve is going to look like this. Okay, so from 0 to 2 pi, the slope of this sine x look like this. Okay, and then we're going to repeat every 2 pi. So what kind of curve does it remind you? What kind of function? The curve from 0 to 2 pi looks like this. What function?
Cosine?
Cosine x, right? Yeah. So yes, cosine x. So our guess over here is the derivative of sine x is cosine x. If you put a person over here, so you have this. Okay. So we guess that the derivative of sine x is equal to cosine x. Now we didn't prove it. Okay. We can actually prove this by using the definition for derivative, the limit of this quotient over here. And then we'll have the limit of sine of x plus h minus sine x over h. And then we use the sum of angle formula, okay? And you can take out sine x, etc. And then at the end, we're able to prove it, that's equal to cosine x. So the proof of this is in the book. So indeed, the derivative of sine x is equal to cosine x. It is proven. Now, we want to use this formula, the newly discovered formula over here, to differentiate this function here. Now for this function, it is a product, right? It's this function times this function. So we're going to use the product rule to differentiate that. Okay, so we're going to differentiate the first function, the x squared function, and then times the second function over here, adding the first function times the derivative of this second function over here. So that's the product rule. So differentiate x squared over here, we get 2x. Now times this sine x, and then adding x squared over here times, what's the derivative of sine x? We just discovered. What's the derivative of sine x?
Sine x.
Cosine x, right? So times cosine x, and now we are done. Okay, now we're going to discover the derivative for cosine x, okay, similarly. So we draw the curve for cosine x, okay, so this is the curve for cosine x from 0 to 2 pi, it looks like this. Now we're going to look at the slope of the tangent at each point on this curve. At this point, and this point, and this point, the slope of the tangent, they are going to be equal to 0 because the looks like the tangent line are horizontal. So we're going to have at this 3 point, 1, 2, 3, y coordinate equal to 0. That's the duality. And then at this point and this point, the slope here is right here is -1. The slope over here for the tangent looks like it's a +1. So I have here, we'll have y to be -1 here, y to be +1 over here. And if I draw the curve over here, that will look like this, okay, from 0 to 2 pi. So what does that remind you? Now, sine of x over here looks like this, from 0 to 2 pi. Now this one over here looks like is the sine curve over here turning upside down, right? You flip it over the x-axis. So turn this sine curve upside down, you get this curve over here. So it is negative sine x over here. So our guess here is the duality for cosine x is negative sine x. We're able to prove this duality of cosine x equal to negative sine x by using the definition. So the proof is in the book. Okay, so you can read over the proof. Now, what about the duality for tangent of x? We know the duality for sine x and cosine x. So we can relate tangent of x and express that as sine x over cosine x. So we can use the quotient rule to differentiate this. According to the quotient rule, we're going to differentiate this function on top. So I'm going to differentiate sine x and then times this function down here, cosine x, and then minus this function on top times the duality of this function down here. And then all of this over the square of this denominator over here. The duality of sine x is what? If you guys know the answer, you guys can shout out the answer over here. The duality of sine x is cosine x, and then times this cosine x over here minus sine x times the duality of cosine x is what? Negative sine x, right? Okay. And then all of this over the square of cosine x. Now over here, negative times negative is positive, right? So this becomes adding the square of sine x. Now looking at this numerator on top, cosine square x plus sine square x, what does this equal to?
1.
Yeah, equal to 1, okay, you got it. Yeah, so that's equal to 1. So this will become 1 over the square of cosine x. Now, what's the reciprocal of cosine? Is secant, okay? So 1 over cosine x is secant x. So this is the square of secant x. So we just discovered that the duality for tangent of x is equal to secant square x. We use the quotient rule to prove that. Question? All right, so use definition of duality. We are able to get the duality of each one of these trigonometric function, okay? So let's put them together, okay? So the duality of sine x is what? Cosine x?
X.
Yes, yeah, cosine x, you got it. The duality of cosine x is what?
Negative sine x.
You got it, negative sine x, okay. Don't forget this negative sign in front. Okay, duality of tangent x?
Secant squared x.
Secant square x, yes, you got it. Duality for cotangent x? Similarly, we can prove that the duality of cotangent x is equal to negative cosecant square x. And the duality of secant x is secant x times tangent x. And the duality of cosecant x is negative cosecant x times cotangent x. Now, I'm going to teach you two tricks to remember this. The first one here is this, okay? So if you start with cosine, cotangent, cosecant, you always have this minus sign in front, the negative sign in front, right here, okay? Another one here for sine and cosine easy, right? They alternate, right? Duality of sine is cosine, duality cosine is negative sine, okay? And now what about tangent and secant? So I have a trick for you to remember. So remember, if you are in the exam and you forget, well, what's the derivative for tangent of x? And then you try to ask your friend, and then your friend will say, "What? How do you say this word? Is it say right? Means be quiet, okay? So, and then it's be quiet, okay? So this one here, this word here, if you take away this p over here, okay, then it's SST. So this SST is going to help us to remember the derivative for tangent and secant, okay? This S here is secant, and then the T here for tangent. So if you try to find the derivative for tangent, you will have this secant times secant, which is secant squared. Okay, so the derivative of tangent x is secant square x. Now what about the derivative for secant x? So the derivative for secant x will be secant x times tangent x over here. You're trying to find the derivative secant x, then you go over here, you see is secant x times tangent x right here. Okay, so that will help you remember the derivative of these two functions, the SST trick I share with you. Now, the derivative for cotangent x, well, this is a co-function of this, right? So since the derivative of tangent x is secant square x, the co-function for secant is cosecant. So you just put cosecant, instead of secant, you put cosecant. So it will be cosecant square x. But it starts with this c over here, then you put a minus sign, okay? Remember cotangent, cosecant, then the derivative had this minus sign in front. And similarly for this, okay, the derivative for cosecant x, this is the co-function of this. Then we try to find the co-function of this one here is cosecant, and the co-function of tangent is cotangent. And then because this is a c here, the trick here to remember is you put a minus sign in front. So that's the SST rule. So derivative of tangent is secant square. The derivative of secant is secant times tangent. So that's one trick I share with you. All right, now let's solve this problem over here. So we're given this function. For what values of x does the graph has a horizontal tangent? So what does it mean that it has a horizontal tangent? Which means the slope of the tangent will be equal to 0, which means the first derivative will be equal to 0 over there. So we'll first we take the first derivative of this function. And because this is a quotient, so we're going to use the quotient rule. So use the quotient rule, we're going to differentiate this function on top times this function down here minus this function on top times the derivative of this function down here. And then over the square of the denominator, okay? So the derivative of secant, remember the SST rule. What's the derivative of secant? Everyone? Derivative of secant is what?
Secant x times 10x.
Secant x times tangent x, right? Okay. So we'll have this secant x times tangent x. And the derivative of this, derivative 1 is 0. Derivative of tangent x is what?
Secant squared x.
Secant square x. We got it. Good job. Okay. So we have secant square x. Okay. Now, when we get to this step, we're going to take out this common factor secant x. So we both have secant x over here. So we take out this common factor secant x in front. And now you distribute this tangent x. Tangent x times 1, you have this tangent x. Tangent x times tangent x, we have this tangent square x. And then minus this secant square x right here. Now, look at this expression in this parenthesis. Tangent square x minus secant square x. We're going to simplify this, use this identity. This two identities, 1 plus tangent square x equal to secant square x. So tangent square minus secant square will be equal to -1 from here. So we're going to replace this by -1. Now we're going to have, this will be tangent x minus 1. So this is the first derivative. Remember, we're trying to find where on the curve, the graph will have a horizontal tangent, right? So horizontal tangent, the slope will be equal to 0. So we're going to set the first derivative here equal to 0. So set the first derivative equal to 0. Now, when you have a quotient equal to 0, that means that the numerator equal to 0 and the denominator does not equal to 0. So we're going to set the numerator here equal to 0. Now, set this numerator equal to 0 by the 0 factor property. We'll have either this equal to 0 or this equal to 0. To solve this equal to 0, now remember, secant is the reciprocal of cosine. So we're going to have 1 over cosine x equal to 0. Now you see that 1 over this equal to 0. See the numerator up here is 1. It's never 0. So is it possible that secant x equal to 0? So it's impossible for this to be equal to 0, okay? So secant x will never equal to 0, okay? See, the numerator here is 1, okay? So it's not 0. So for this equation here, we have no solution. So no solution from this. Now what about this one over here? So from here, we'll have tangent x equal to 1. Now, we want to solve this trig equation. Let's solve this at the first quadrant. Tangent what angle equal to 1? It's already said it over here, right? Tangent of pi over 4 is equal to 1, right? Pi over 4 is this angle at the first quadrant that tangent equal to 1. So, so we have this x equal to pi over 4 first. However, tangent, what's the period for tangent? The period for tangent is equal to pi, right? So it's going to repeat every pi, okay? So if you add any multiple pi to this pi over 4, tangent of that will always equal to 1, okay? So all the solution for this equation here will be pi over 4 adding any integer multiple of pi. So adding k pi over here, okay? So x will be equal pi over 4 adding any integer multiple of pi. So k here will be any integer. So k will be equal to 0, plus or minus 1, plus minus 2, plus minus 3, etc. So any integers. So to answer the question here, the answer here will be when x equal to pi over 4 plus k pi, where k is any integer, the graph of the function has a horizontal tangent. Right? Question for this one? Okay, now number 2. Number 2 over here, we have this spring over here. The spring over here starting at rest is like this. Right, so if you put an object over here, it's going to stretch the spring down here. Note that the downward direction is positive. We consider this position here to be positive. And if you compress the spring, then this S here we consider as negative over here. Okay, so going down is positive, going up is negative. Okay, so this is the position function. So we're given the position function of this object. Okay, so it's 4 cosine of t. The t here is a time. Well, we're trying to find the velocity function of this object. Okay, velocity correspond to the first derivative of the position. So we differentiate this function. So take the first derivative. So differentiate 4 cosine of t. So the 4 here is a constant multiple we bring in front. And then we differentiate cosine of t. What's the derivative of cosine of t?
Negative sine t.
Yeah, so we have negative sine of t. Yes, you got it. Okay. So this is the velocity function. Okay, now we're trying to find the acceleration function. Acceleration correspond to the second derivative of the position function, right? So we're going to find the second derivative of this position function. So we're going to differentiate this velocity here one more time, okay? So the -4, we bring it in front. And then we're going to differentiate this sine of t. What's the derivative of sine of t? Everyone?
Cosine t.
Yes, you got it. Okay, so that will be cosine of t. So derivative sine t is cosine t. Okay. Now, in your homework, they also ask you for the speed. Okay. So you find the velocity function and then also the acceleration function. But what about the speed? The speed is the absolute value of the velocity function. So you just take the absolute value of this velocity function. Taking the absolute value of this, the absolute value of -4 here is +4. Okay, so we have +4. Now, sine of t or negative sine of t, we don't know about the sign, so there's no guarantee it's positive. The 4 here is always positive, so we can bring it in front of this absolute value. Then the rest here, we don't know is positive or negative, so we have to keep that inside the absolute value. So sine of t will be inside this absolute value over here, and that's how we simplify this. So we take away this negative sign, and then we have this. So the result here will be always positive or at least 0, right? Okay. Okay, now let's try to discover a pattern, okay? So what's the derivative of sine of x when you differentiate that one time? Okay, everyone?
Cosine of x.
Yes, cosine x. Okay, now let's differentiate this one more time. What's the derivative of cosine x? Negative sine of x? Yeah, you got it, negative sine x. Okay, now let's differentiate this one more time. Okay, what's the derivative of this? So you have this negative sign in front. What's the derivative of sine x?
Cosine of x.
Cosine x. Okay, differentiate this one more time. You have this negative sign in front. The derivative of cosine x here is negative sine x. Now you're right. So when you have this negative and negative here, and they cancel, and it becomes sine x. So now you discover there's a pattern. When you differentiate sine x 4 times, you get back sine of x itself. So it has a cycle of 4. So using this pattern, we're able to find higher derivative of sine x. What's the x derivative of sine x? You see over here, when I put a parenthesis here, that indicating this is the x derivative of this sine function. What's the x derivative of the sine function, sine x?
Sine x?
Yes, it's sine x, okay? Because it has a cycle of 4. So we're going to get back sine x itself because this is a multiple 4, right? Okay. What about the 10th derivative of sine x?
Negative sine x?
Okay, very good. So we can take out any multiple of 4. In computer science, you use this function, mod a lot, right? Mod over here is a function that gives you the remainder. So when you divide this by 4, the remainder over here, you get 2. So we take away all the multiple of 4, then we'll have the 2 left. So this will be the same as the second derivative of sine. The second derivative of sine, if you look over here, will be this. So it is negative sine x. Okay, so you have this pattern. Now you can tell the 100 derivative of sine x. What's the 100 derivative of sine x? Anyone?
Sine x?
Yeah, it's sine x because 100 is a multiple of 4, right? Okay, so that's an interesting pattern. Okay, now let's discover another pattern here. So cosine x, differentiate that one time. What do we get? Anyone? Negative sine x, right? Okay, differentiate that one more time. Negative what?
Sine x.
Cosine x. Differentiate that one more time. Differentiate that one more time. So this negative sign here carry. The derivative of cosine x is what?
Negative sine x.
Yes. guys are tired. Negative sine x. So then you have this negative sine x here. Negative times negative is positive. So this is equal to sine x. Now we differentiate sine x, then we get cosine x. Again, you see that if I differentiate that 4 times, I get back cosine x itself. So it has a cycle of 4 again. So what's the 12 derivative of cosine x? What does it equal to?
Cosine x.
It's cosine x, right? Because 12 here is a multiple of 4. What about the 13 derivative of cosine x?
Negative sine x.
Negative sine x, good job, okay? So if you take away all the multiple of 4, if you mark 4 to this, you get 1. So the 13 derivative of cosine x is the same as the first derivative of cosine x, which is going to be negative sine x. All right, okay, good job. All right, this is the last one over here. Do you guys remember the limit of this quotient? The limit of sine x over x as x approaching to 0. Anyone remember? What does it equal to? Remember, I tried to help you remember by graphing it. And then I'm trying to also show you using the calculator 3 different ways. You guys remember? See, if I graph this using decimal, the graph of sine x over x look like this, okay? It's undefined over here. Remember, we use decimal, okay? The limit of this, if you're looking at the graph over here, if you're approaching this function from the left and from the right, the function value is getting closer and closer to 1. So the limit of this is 1. Remember, you use radian for the x right here. We can also try to understand this by looking at the unit circle, right? Last time I talked about that. So if you have a unit circle over here, the x over here is correspond to this central angle over here. Then because this is a unit circle with radius 1, then this arc length over here will be equal to x also. The length of this will be x. See, the circumference of this circle is 2 pi. This angle over here, if you go around this 1 time, it's also 2 pi. So if this angle is x here in radian, then this arc length here will be x here also. Okay, so this arc length will be x. So sine x here is the pink one over here. Okay, because opposite over hypotenuse is sine. So opposite here over 1, so this is sine x over here. So sine x is this pink one over here. X over here, you can imagine is this arc length over here. Okay, so what does this limit over here means? When this angle here, x is small, then this sine x, the pink over this arc length over here, the ratio is going to getting closer and closer to 1. So they're about equal. So you can try to calculate this with calculator, okay, in radian mode. So if you have sine of 0.001, and I think last time some of you helped me to calculate this, right? And it turned out to be 0.000999, etc. Okay. And now dividing by 0.001, looking at this is about 0.001, right? It's about, now this quotient is about equal to 1. So the smaller this angle over here in radian, then the ratio over here is going to be getting closer and closer to 1. So the limit of this ratio is closer and closer to 1 as this angle here, as this x here going to 0. Another way to write this limit here, instead of using x, you can also use theta, okay? So theta. So limit of this ratio is equal to 1 when theta approaching to 0. Now we're going to use this important limit over here to find this limit, okay? Now, sine of 7x over 4x. Now notice that this this don't match. This is 7x, this is 4x, okay? Over here, in order to use this limit here, it has to be this angle and this have to match. Data, data, and here has to be data, right? So let's put it down over here. So we have this sine of 7x. Let's try to think about this one here as data. Okay, so think about that as data. So down here, I want to have data to match with it, right? So I need to put a 7x over here. So to match with this. Okay, so this 7x here, I put over 7x here. But I didn't have a 7x here before. So if I divide by 7x, so I will multiply back 7x over here. And now over this 4x. So the trick over here is to try to match them. You have a 7x here, then you would divide by this 7x over here. But later on, you multiply this 7x back. Okay, so that's the trick. Okay, now what happened over here? So think about this as data. So you have sine data over data. When data approaching to 0, the limit of this will be going to 1, right? So, but this is not 7x, but think about this. When x approaching to 0, what happened to 7x? Does 7x go to 0 also?
Yes.
Yes, 7x will also go to 0, okay? Over here, so we have limit of sine data over data as data approaching to 0, okay? Then we can use this limit over here, right? Okay, so that's the trick, because you have to match this two. So now over here for this, you can simplify. This is 7 over 4. In fact, you don't need to put the x over here. You can just put 7 over 4, okay? So 7 over 4 here is a constant multiple. So 7 over 4 over here is a constant multiple. So you put that in front right here. And then limit of 7x going to 0, sine of 7x over 7x. And this limit here is equal to 1. Okay, so that's equal to 1. Now you have 7 over 4 times 1. So the limit over here will be equal to 7 over 4. So remember this sine 7x over 7x, when 7x going to 0, that's equal to 1. So that's why I got 1 over here, okay? And then this constant multiple over here, you bring it in front. Okay, just one more example, okay? Now we know that sine of data over data, as data approaching 0 is 1. Let's take the reciprocal of this. So this time I put data on top, sine data down here. As data approaching to 0, what is this limit over here? Anyone? Well, this is the reciprocal of this function. So the limit will be the reciprocal of this. What's the reciprocal of 1?
Is it just 1?
It's 1 itself. Okay. Sometimes the easy question is the one that you might wonder, is it right? Right? Reciprocal 1 is 1. Okay. So that's also equal to 1. So both this and this are equal to 1. Okay, now we can use that to find this limit over here. In your homework, you have something like this. So when you see this sine 2x here, and then we might use one of these two limit over here. So I put sine 2x over here. But for the tangent 6x, we can express this as sine over cosine, right? So that will be sine of 6x over cosine of 6x. Tangent is sine over cosine. Now we're going to do the mix and match, okay? So we have this sine of 6x over here. So let's put it down. So sine of 6x. Now because this is 6x, I'm going to match with that. So I'm going to put down the 6x over here. But if I divide by 6x, later on, I multiply back 6x. Now I have this sine of 2x over here. I'm going to match this up here with the 2x over here. So 2x over sine of 2x. But if I times 2x here, I need to divide by 2x right here. Okay. Actually, I want to use a different color. So I'm going to use a blue. So I'm going to match with the 2x here, and then now divide by 2x over here. Now that would take care of this one and this one. And what about this cosine 6x? Well, it's going to stay in the denominator over here. So 1 over cosine 6x. Now, after this, look at this quotient over here. Sine of 6x over 6x. As x approaching to 0, 6x also approaching to 0. So this is kind of like sine of theta over theta as theta approaching to 0. What does this quotient approaching to? What's the limit of this quotient?
1.
It's going to be 1. So we have 1. And then similarly, what happened to this quotient? It's going to what?
Go to 1.
Go to 1. Okay. And what about this one over here? Now, this one over here, when x approaching to 0, we can go ahead and substitute 0 into x. So it's 1 over cosine of 0. Okay. Cosine of 0 is going to be 1. So that's 1 over 1, which is equal to 1. Okay. Now what about this one? This is just 3. Okay. So finally, we have 1 times 1 times 1 times 3. So that's equal to 3. So you just need to match them. Okay. Last one. I know I go over a little bit, but just for you to help you with the homework. Okay, now what about this? Cotangent x over here, you can express this as what? Cosine over sine. Now you have this x over sine x, we're gonna match them, okay? So these two, we're gonna match them together. And I'm leaving the cosine x here by itself, okay? So when x approaching to 0, this quotient is approaching to 1. And cosine x is approaching to what? When x approaching to 0, cosine x going to cosine of 0, which is equal to 1. So that goes to 1. So the limit of this will be 1 times 1, so that will be 1. Now, this problem here appear in the homework. So I want to just give you a hint, okay, before you do it. So we're trying to find the limit of this quotient, sine of x to the 8th power over x as x approaching to 0. So we have this sine of x to the 8. So to match with this, so what should I put down here? Anyone?
X to the 8.
You got it, x to the 8th power. But then I have to multiply x to the 8th back over here, right? And then now the x here, this over x, you put it in the denominator, okay? Now just do a mix and match, okay? So match with this and then later on multiply back. Now the limit of this quotient as x approaching to 0, this is going to what? What does this quotient go to?
1.
Yeah, you said 1? Yes, it goes
Yep.
to 1, okay? And then what happened to this? X to the 8 over x is equal to x to the 7th power. As x approaching to 0, what does x to the 7th power goes to? It goes to
0.
0. Now you have this 1 times 0. Okay, the limit of this is 1. The limit of this is 0. So you have 1 times 0, which is going to be 0. So that's how you do your homework. Right? So just give you a hint for this homework problem. The lesson ended. Okay, any question?